So we have one announcement, a couple of announcements first before we start the chapter 3. First one is Drew and John, right? John, it was originally John who came up with this idea, right? Last lecture. It doesn't matter. They had the idea that we can solve this shock location problem analytically. And I haven't gone over his proof yet, but Drew has given me a proof of this.
That's a loose word, proof, right?
I mean, the solution. Yeah, a solution is probably a better thing. If there is no error in his solutions, I was expecting to get something from you as well.
Yeah, it's not that good.
Yeah, you can give it to me after the class. If their solution is correct, then they don't need to take the final exam. That was the idea, right? If you make it, they came up with this claim. So, but that the point is that the reason I'm sharing this with all of you is if you come up with any bold claims in a class, and if you can prove your claim is correct, which may happen, like it is not very out of imagination, I guess, you will be able to get 100 on your final exam, right?
Wait,
without
they
even
made that claim, or was that something that you assigned?
No, they made a claim in class.
Okay.
And his rough draft, I couldn't really say no to. I couldn't really find any error in the rough draft. But he has solved this. True, right? And I assume I have a solution from John as well. And yeah, these things happen in my classes. Just for those of you with this, I mean, a lot of you have had a class with me, so you have seen these type of things before. Those of you who have this is their first class with me, just be on the lookout. Challenging the authority is appreciated in my classes. That's the point. Except for the mask rule. I mean, that is not my rule. If we didn't have the mandate, I wouldn't have worn the mask because I'm double vaccinated, right? Well, that's a different rule. Yes. Oh, yeah, I always forget about the projector. And the second announcement is your homework is posted. It was posted earlier today. So it is, yes. Homework 4, yes. And you have 1 week to submit the solutions. We will go over all of chapter 3 today. The reason chapter 3 is a very small chapter. It doesn't take that much time to go over the chapter 3. And then we will spend Monday solving some example problems and talking about the exam, right? Which is going to be the Monday after next Monday, so November 1st, right? And on Wednesday we will start chapter 4. Okay, this chapter 3 is essentially an introduction to chapter 4. Think of it that way. If I wrote this book, I would have included this as the first part of chapter 4. I don't know why it is a separate chapter. But yeah. Also, one since all of you are either in lab 1 or lab 2, I'm taking all of the lab 1 students to do a lab tour. This is essentially going to be the part of the class from now on, right? So every lab 1 student from now on is going to get this lab tour. And this is the research labs tour. So we are going to go see all of the research labs that do aerospace research, right? If lab 2 students want to do something like this, we can definitely organize this for you as well, right? How many lab 2s? We have 4 lab 2 students in the class, right? Yeah. If you think this is something, we are going to, I don't know the name of the labs, but we are going to do a tour of the propulsion lab, the exam, and also the, I guess, composites lab, LOTS lab, and also 3D printing lab. Yeah, that's a better name for it. And also the what other lab? Drone lab, if you will. Dr. Vizialis's lab. Nikos Vizialis. So if it's something that interests lab 2 students, Also maybe additive manufacturing lab. 4 labs, right? Something that interests you, we can definitely do it for you as well. Okay? We are basically done with lab 2 material. This was the last one. If we get the new wind tunnel, we will have another physical lab, but the rest of the labs are going to be just numerical, CFD. So we essentially go do 1 lecture. There is no labs anymore. We just do the project, submit your project, right? Okay. I guess that's it. Is there any questions about anything, about the exam, about the homework, about the whatever, about the machine design?
Oh, when can we, like, the exams graded, like, grade?
I'm sorry, I should have graded much earlier, but I will try to get it as soon as possible.
Yes.
Right?
I'm
But
in a rush to see bad grades.
bad grades? That was an easy exam, wasn't it?
It was, but I've come to expect that.
When you become an
Easy
engineer,
things, I'm not good.
when you're an upperclassman in engineering, you don't have high hopes.
Yeah. I guess
It's not
that's
the
nice.
easy stuff.
What I couldn't.
When you're an upperclassman in engineering, you don't really have high hopes, because even if something seems easy, there's always a trick.
You messed up something.
You always messed up somewhere that thing.
That's right. No, I agree. But let's see what happens though. Let's see what happens. Don't be hopeless, I guess. Always keep hope. So for whatever reason, I don't really want to start chapter 3 today, but
Let's just do chapter 4.
no, I don't want to start teaching. That's the point. Okay.
You don't have to.
We can talk about our engineering experiences. Video time.
Let's.
I can ask a question about the lab if you want.
No. It will be done in less than 45 minutes. So we can spend the last part of the class talking about whatever, right? Or you can leave if you want to. If you don't want to see me anymore, you can leave. Okay, so chapter 3. Let's start the chapter 3 discussion. Chapter 3, its official name is Engine Thrust in the book. Engine thrust and performance parameters. Essentially, in this chapter, we are going to learn how to calculate thrust of a jet engine and also how to analyze or how to compare the performance of one engine with another engine. So essentially, we are going to learn how to calculate a force, which is thrust, and also efficiency, all of those other performance parameters, right? And this is going to be our link to our key to connect whatever we have learned in the cycle analysis to the jet engine design, right? So all of those analyses are going to end up with thrust calculations, all of the performance calculations, right? That's the idea here, right? So, aircraft engines in general are designed to produce thrust. That's the idea here. That's why we want to calculate the thrust. But before going to thrust calculations, let's have a general schematic of a jet engine, and let's become familiar with the nomenclature here, because this is something we are going to need. We are going to name the unperturbed ambient. Unperturbed ambient. This is going to be your station 0 or a station 0, right? Then the inlet of the jet engine is going to be the station 1, right? From the inlet nozzle to the inlet of the compressor is 1 to 2. So this station 2 is always the inlet of the compressor. If you have a multi-spool configuration, then you're going to have a high pressure compressor and a low pressure compressor, right? Low.
I'm sorry, what does that say, Professor, for the number one?
This goes to number 0, unperturbed. It is not perturbed. How do we write this? Unperturbed. So we have the low pressure compressor here, LPC. We have the high pressure compressor here, HPC. And then the exit or the outlet of the compressor is going to be station 3. If you only have 2 stages of the compression, the outlet of the low pressure compressor and the inlet of the high pressure compressor is going to be a station 2.5. If you had 3 of them, I would name them 2.A, 2.B, and 2.C, right? But essentially it's going to be something between 2 and 3, right? And then we have the combustor. That is between station 3 and station 4. And then you have all of the turbine stages. Maybe I should. I'm just going to. Since this is a multi-spool configuration, we are going to have a high pressure turbine. And then after station 4.5, we are going to have a low pressure turbine. So turbine is going to be between station 4 and 5. Combustor is between station 3 and 4. And then between 5 and 6, let's actually do this. It's going to be the distance between the turbine and afterburner. This is where you inject more fuel to your system. Then you have the flame holders and all of those stuff, right? And 6 and 7, between 6 and 7, you have the afterburners. Afterburners may not be present in all of the jet engines, right? Or maybe turned off, right? But it doesn't mean we are going to hold their numbers anyways, right? So it doesn't matter if you have an afterburner or don't have an afterburner. 6 and 7 are reserved for afterburners. And then we have the convergent divergent nozzle at the exit. We are going to have a throat of the nozzle, which is always station 8. And also the exit of the engine is going to be a station 9. This is the most common numbering scheme when it comes to jet engine station numberings, right? There are different schemes as well, but this is the most popular one, and this is what we are going to use for most of the class. Okay, for most of this class. So again, station 0 is your ambient condition. Station 9 is your exit condition, and whatever is in between is going to we're just going to go by order of the hitting the inlet air, I guess. So we're going to have the inlet and then the compressor, then the combustor, and so on and so forth. Yes.
So when you hear about engines having like 2 low pressure compression stages and like 2 high pressure compression stages, what does that look like on that? Is it like staggered? You go like LPC,
Yeah.
LPC, LPC?
Depends on the, but we are not talking about the very modern engine configurations here. On the classic ones, it essentially means that you have 4 stages, yeah. Okay. Yeah, they are going to be just back to back. Okay. If there's no question about this, let's move on to finding the equation of thrust. Okay. So, how can we find the equation for thrust?
Equal to
No. Your perspective is not wrong. Your perspective is not wrong, but your perspective is from a flight mechanics perspective, right? We are looking at it from a propulsion perspective. So we want to calculate thrust that is produced by the jet engine. At this point, we don't really care about lift or drag or anything. Thrust is going to be something that is an inlet, that is going to be given in flight mechanics analysis, right? So let's say we are only looking at the engine. Yeah.
Is it derived from mass flow rate then? Mass flow rate of exhaust?
How would you calculate? How would you relate mass flow rate to
Exhaust velocity.
exhaust velocity, momentum? Okay. So essentially, based on what, did you want to add something?
I had something real quick.
Okay, that's all right. So based on what I heard from your classmates, Drew and Nicholas, we need to use the governing equations, the fun parts, right, to find the equation of thrust, right? What are the two main governing equations we are going to use here? The conservation of mass and the momentum equation. Essentially, conservation of mass tells us that whatever mass is going in is going to go out of the system, right? Mass is not created nor destroyed, right? That's the idea. And momentum equation is going to tell us that all of the forces are going to be equal to momentum of the system, d mv dt. That's the idea, right? For our case, usually m dot is the case, so dm, we are going to assume the velocity is constant and momentum is calculated like this. But where do we apply these concepts? How can we apply this concept? Let's say you have this jet engine. A very bad drawing of a jet engine. I'm not good at drawing, right? I guess this is why I'm not a design person. But yeah, let's say this is your jet engine and your flow is coming in. This is going to be the stream tube that is going to go into the engine, right? And we also have the outlet. What we are going to do is that we are going to have a control volume that is going to encapsulate this stream tube and as well as the jet engine, right? Here we have rho naught, v naught, or rho 0, v 0, that's the velocity, and that's essentially the flight velocity, right? That's going in, and the amount of air that is going inside the jet engine is going to be m dot naught, right? And whatever mass is that's coming in from this other side is going to be named m dot surroundings, right? Very inconsequential, doesn't really matter for us at this point.
Is MS like the bypass ratio?
No, we are not talking about bypass ratio. We will talk about the bypass ratio in the bypass ratio only comes in when you're talking about the turbofans or turbofans, right? That's the idea. And we are not talking about the different types of engine yet, jet engines yet. That's chapter 4 mostly. Okay. And let's call the velocity going out V9 and rho 9. What is the outlet m dot here? What is the m dot that is going out of the system? M naught plus, let's say just m that is going out of the engine. Plus m dot of the fuel, right? Because we also are adding fuel to this. Right? Okay. And for the rest of it, the flight velocity is going to be sustained, right? From the outside of it. Okay. So We can, based on this analysis, we can let's write the momentum equation first. Or let's actually write the conservation of mass. What is the mass that is coming in? We have rho naught v naught a, which is m dot naught, right? In this stream fluid, this a is going to be this area, right? Plus m dot surrounding, m dot f. This is the inlet mass. And then what is going out is going to be m dot naught plus m dot f plus rho naught v naught a minus a9. That's the area of this station 9. And this part, I guess this is just this area for the inlet, all of it, right? This is going to be the conservation of mass. M dot in is equals to m dot out. What is coming in? This is coming in from all of this. This is coming in from the surrounding. And m dot f is coming in from the fuel injection, right? What is going out here? From these sides, your area is going to be a minus a0, a9, which is your exit, right? Multiplied by rho naught v naught, right? This remains unchanged. That's the idea. And for the rest of it, we are going to have m dot naught and m dot f, which essentially means that we can play with this a little bit. We are going to get to this. M dot of s is equals to m naught minus, this is something that we can actually figure out very easily, right? These two equations. Conservation of mass. But this doesn't give us any information about the thrust, right? There is no force here. So we have to use the momentum equation to find the thrust here.
What's the subscript on A again? Is that Q?
This is 9, station 9, exit.
Oh, not. Oh.
9, number 9, yes.
So why are we, for the n dot in, or n dot not, beginning, we use the whole area. How does that not include the n dot s, if that's?
M dot s,
Like include n dot s?
no, M dot s is the incoming mass from these sides.
Okay, so it's
The
not
top and
included
bottom.
So it's not included with that n dot basically? Okay,
No.
I thought it was counting it.
No. So this, we could have said this is m dot naught plus rho naught v naught a minus this area, this stream tube area, but we don't know what that area is, so that wouldn't have made anything easier. Okay. So let's write the momentum equation. For the momentum equation, we have sigma of m dot, and we are writing this in the x direction, as the thrust is only in this direction, right? That's the idea. The momentum out is equals to momentum in, and this is equals to sigma f in the x direction of the fluid. Again, we want to find an equation for the thrust, right? This can give us an equation for the thrust, right? Because the thrust is going to be hidden in the forces, sigma of the forces. So let's actually expand on them one by one. M dot Vx out is going to be equal to the momentum that is going out of the system. So it is going to be m dot naught or m dot 0 plus m dot f multiplied by the exit velocity, which is v9. Do we have anything else here? The momentum of the outgoing flux, huh?
The momentum of the outgoing.
The outgoing fluid. The outflux, whatever, I don't know what to call it. The momentum of the outlet of this control volume.
Exhaust or no?
We already captured the exhaust of the jet engine, right? Is there any outlet of this control volume, for this control volume? This part, right? This is not m.s. m.s is for this. That is because of them. Some m.s is contributing to it, essentially. That's the idea. How can we calculate this momentum? So this is coming in. This is coming in, right? These are all the inlet. What happened? No, nothing here. It doesn't let me write them.
Rho V and then the delta of the two areas.
I'm sorry. Don't know why they do that. It doesn't let.
Click that hand kind of thing on the top.
But it doesn't let me click. Okay. Yeah. Thank you.
Happened to me a lot.
Yeah. That's idiotic. But yeah. What did you say, Nicholas?
Is it something to do with the difference in the two areas?
I guess so. Yeah.
Is that the second part of that? The Rho V?
Or the EFI minus A9?
This is only the m dot though. M dot of that part, right? How can I multiply by the velocity, right? Exactly. So we're gonna have rho naught v naught, or rho zero v naught, v zero a minus a naught multiplied by v naught, which is going to be the velocity at that location. Okay. So let's do this momentum analysis for the inlets. What is coming in here? M dot naught, M dot S. So you just multiply M dot naught and M dot S, is that?
You need the velocity.
So what is it? M dot naught, or let's not do the M dot, let's just do, this was the inlet, right? From this part of this control volume, right? This is the M dot. Just multiply it by the velocity. So rho naught v naught a multiplied by v naught. And for that m dot s, your velocity, we are going to assume your velocity is v naught as well. Are you guys following, or is it? Yes? No? Where is the question?
Right now, I don't even know what I'm not knowing. I don't know. I'm just gonna follow through and.
Okay, so let me tell you this, because this is a very easy analysis, right? But most of our students can't follow this, especially in ME, because we don't really do any momentum analysis. This is just find the inlets and outlets, find the momentum of it. That's a very easy, and this is something, understanding this concept, I'm pretty sure is going to help you in the future, right? There is no differentiation, there is no integration, there is no advanced mathematics. You just have to understand the momentum equation and these concepts, right? So because I know that a lot of students don't understand this, I am going to give you one question specifically about this. So I'm going to give you some values, a control volume, and I'm going to ask you to write the momentum equation, and using that momentum equation give me the final thrust. Okay? Does it make sense? So this is something
What part of will you be given in the equation?
I will give you some values here, and then I will ask you to write down the momentum equation and calculate the thrust. Okay? And the final thrust calculation is not going to be that important, but the procedure is going to be very important. I just want to make sure that you understand how to do this.
So it would basically be like just writing these equations and then kind of plugging everything in.
Yeah, exactly. So essentially you want to start from here, find all of the inlet momentums, outlet momentums, and all of the forces that are applied here. Okay. And I will probably solve something that is similar to this, I guess, in the class next week. Right? So, and now it's time for the forces in the x direction. What are the forces we have in the x direction? Of course, we have one force, which is a thrust force, that is going to push the fluid in this direction, right? So it is going to be a negative force, right? Let's call it the fluid, F of fluid at this point. What is the other force that is present here?
Drag.
We are not assuming any friction here, so the friction drag is not present.
Does the combustion have anything to do with it?
No, we are not looking into the jet engine at this point, right? We are looking just at outside the jet engine. What are the different types of drag that can be present here?
Wave drag,
Pressure drag?
Why wave drag?
because it might be shock waves, right, it's just coming out of the sun.
No, wave drag is not going to be acting at this scale, right? This huge scale.
Pressure drag?
Pressure drag, right? We have two different pressures, right? Pressure drag. Or in other nomenclature that we have discussed, pressure force, right? We have talked about pressure force before, right? So how can we calculate this pressure force? Is going to be pressure at the exit station minus your ambient pressure multiplied by your exit area. So what do we have here? We have the total amount of forces that are present. We also have the outgoing and incoming momentum of the system. But let's see if we can use this formula to simplify this a little further.
Is that basically saying that the pressure is almost pulling it forward? Is that what, we define X going that way, negative X is that way, right? So is that saying that we're pulling it forward almost? Or, no, the pressure's not, it would be less than the pressure is not. It just seems like it's pulling it. If it's negative, it would be pulling it, almost like sucking it in.
I mean, this value can be negative, right?
It can be
So it
negative.
can. So that doesn't really say anything about the force,
But
as
there's a
long as.
negative in front of it, so if that value is negative,
Let's do this then. Does it change your perspective now? So it's just a number, right? Since we don't have any information on the pressures at this point, you can't really make any conclusions for that one.
it just seemed like it is pulling it forward with the pressure.
Yeah, I understand where you're coming from, but since we are not talking about this force needs a little bit of calculations inside of it, right? We have to have pressure information, right? So you can't make that conclusion. And this is also about this. We can't also make that conclusion for this as well. This is just a sign convention. So I want to say the reason I have this negative sign is here to make sure in the future we're going to have positive sign for f, right? That's it. So eventually, wherever you see on a vector analysis, whenever you see a negative sign, it doesn't mean anything. None, right? Why doesn't it mean anything? Let's say you have negative f is equals to ma. Your a is 2, your m is 3, right? Your force has to be negative 6, which essentially means that your force is in the other direction that you had assumed. So this formula has to be positive, right? So it's just a negative sign for a vector is just the direction of it, right? Don't get consumed by a negative sign before a vector, right? Doesn't mean anything. Because that vector itself can always get a negative value to circumvent that negative sign, right? And it doesn't change the magnitude of that force. It's just change the direction of the force, right? It's just a convention. Yes?
Sometimes on some occasions, some planes are using like thrust brakes, kind of like their engine shutting down to direct the thrust to slow down the airplane.
That doesn't have anything to do with this. That doesn't have anything to do with this. This is just a mathematical manipulation. Don't get bogged down with this, okay? Okay, so we can use this to simplify our equation here, right? We can just, instead of m dot s, we can just m dot naught. We can have m dot naught, rho naught, v naught, a9, right? We can just substitute this for m dot of s, and then we can plug it into this main equation and simplify it. I'm not going to go over that process, pretty sure you can figure this out yourself. But eventually your F is going to be equal to m dot 0 or m dot naught plus m dot F V9 minus m dot naught V naught plus P9 minus P naught A9. So, your force in the x direction can be calculated using this formula. This is going to be your total thrust. This is your exhaust. How do you write exhaust? Exhaust momentum. This is your inlet momentum. And for whatever reason, this part has a very creative name of pressure area. Very creative. Okay, so what this is telling us is that your inlet momentum is going to decrease your overall thrust, right? Higher flight velocity is going to result in everything else kept the same, is going to result in lower engine thrust, right? That's the idea here, based on pure mathematics, right? What can we say about this one? And I mean, higher exhaust velocity is going to give you higher thrust, right? That's essentially the goal. You want to increase the exhaust velocity with keeping the inlet velocity constant. And I mean, you can figure this out just by looking at this. But what can we say about this? This can have three different situations. P9 is equals to P naught. P9 larger than P naught. And P9 is smaller than P naught. What is going to happen to our pressure area if P9 is equals to P naught? It's going to be 0, right? Essentially, your outlet pressure, your exhaust pressure, is going to be equal to your ambient pressure, right? It is not going to have any effect on your thrust, right? This situation is called perfectly expanded nozzle.
Is this one of those like properties that it depends on the objective of your engine as to which of these conditions you want? No, yes and no. Let's move on. Let's talk about this. And if you still have the question, we'll come back to this, right? When your P9 is larger than P0, you're essentially contributing to your thrust positively. This is called the underly, or under expanded nozzle. And this is called over expanded nozzle. Okay. Why do we call this under expanded nozzle? Where does this come from? Perfectly expanded nozzle. What? Yes.
I'm gonna guess in a perfectly expanded nozzle, they're coming to an equilibrium point, But, and then if it's since we're providing positively, when it's under expanded, that means that P naught, our P9 pressure hasn't come to a settlement, and that's why we're.
So what's going to happen? Let's say, what can you do with that pressure, with that extra pressure, right? When P9 is higher than P0, we have some extra, I mean, it is not a very good naming, but extra, yes.
Would it be possible that it would speed up the combustion process?
Speed, this is the exhaust pressure, right?
Yeah.
So this is after all of this. But my question is, why do we call this under expanded?
Also, it's tight. Higher pressure on the exhaust.
It is, it is when you have higher pressure at the exhaust, we call it under expanded. Why is it? So what happens? Essentially, under expanded means that we can expand it a little more, right, to get to that perfect expansion, right? Okay. So higher pressure, yes.
Why would you want a perfectly expanded nozzle? Your results in less thrust.
That's the good question. That's the golden question that we wanted to get to, right? Why do we want to have a? I mean, there are situations that you don't want to have a perfectly expanded nozzle, but I mean, you can understand from the naming, a perfectly expanded nozzle in most cases is a perfect condition.
Is it kind of correlated to the exhaust momentum?
Yes. How?
So like if we have a under expanded nozzle, we would have less of an exhaust momentum.
Okay, that's a very good point. So essentially, what is going on in a, let's say you are in a supersonic flow, m larger than 1, right? And you have this type of duct. What is the velocity here?
Much greater than 1?
M2 is going to be larger than M1. Supersonic, right? Right? Is it true? Well, what can you say about the pressure?
It's going to be less.
Pressure is going to be
Less.
less, right?
Because velocity increases.
Is that acceptable? Okay. But let's say this was expanded this much. How could you compare M3 for this duct, this type of duct, with M2?
The pressure is going to increase or decrease more because the velocity is going to.
What can you say about M? At this point, let's just talk about the M3. How does M3 compare to M2?
It would be lower.
M3 is going to be lower than M2, right?
Pressure is higher.
Which means that you have a higher pressure. So, essentially, you still have room to expand your duct a little more, right? To get a higher velocity. Okay?
Is it like the nozzle?
What's that?
Never mind.
Okay.
So you
Does this make sense? That's why we call it under expand, because there is still room for expansion to get a higher exhaust velocity. And that higher exhaust velocity is going to provide more thrust for us compared to this pressure area. Right? What's that?
I didn't word it as well, but that was what I was getting at earlier.
Yeah. Okay. So, and when you go past this point, you have overexpanded your reach essentially. Your exhaust velocity is not going to increase anymore, right? That's the idea. So you're decreasing the pressure, you're losing some thrust, you're losing some pressure area, but you are not increasing your exhaust velocity. Yes.
And we're just talking about the static pressure at this point, right?
We are just talking about the static pressure. That's correct. Yeah. And okay, so, but where does this happen? Where can we have this over and under expansion? Can we have it in the subsonic flows?
I don't see why not.
We have one yes and one no. Could you elaborate?
Doesn't in subsonic it like the Mach gets lower as it goes through? So.
As it goes through a
I guess it goes through
diffuser, right?
Yeah.
But we can't have a nozzle though, right? A subsonic nozzle at the exhaust, right? No? Let's actually let's forget about the reasoning behind this. Let's just stick to it because it's going to take a lot of time. This usually happens in subsonic and some supersonic cases. Yeah, we have already had too much theory for today, so. And these two cases only happen in supersonic conditions. Okay. So we already know how to calculate thrust and everything else. Yes.
So in like planes that change their nozzle shape, is this like, is this what they're changing between like under expanded and vertically expanded?
They are changing the exhaust velocity, not necessarily the under expanded. It depends on the velocity at that point, right? But they are definitely changing the exhaust velocity, not necessarily the pressure area though. Depends on the flight regime. Okay. So, I have a feeling like that you guys are very confused. Some of you. No? Okay. For once, no. That's good. Let's not just, let's continue. This part of this we are going to call the gross thrust. And this part is, since it's a force in the other direction, this part is a drag and it's called the ram drag. Okay? So, for a perfectly expanded nozzle, in a supersonic condition, your thrust, which is usually named F of N, is going to be your gross thrust, F of G, minus the ram drag.
Why do things have so many names?
They just have two names though, gross thrust and ram drag.
Why do they rename them though?
What's that?
Why do they rename them if it's the same equation?
How did we rename them? This just has the one name.
Yeah, but it was inlet momentum.
It wasn't the name, it was the type of the thing. The type of it is a momentum that happens at the inlet, right? Its name is ram drag. Okay. Let's see. This thrust is also called uninstalled thrust. Uninstalled thrust. Who can tell me why this is called the uninstalled thrust?
It's just missing other pieces of the puzzle, right?
Exactly. It is not installed on an airplane yet, right? That's why. So essentially we are missing the pylon's drag, we are missing the engine nacelles drag, all of those things, right? We don't have any of those. That's why it is called the uninstalled thrust, right? Let me see. Let me give you, let's do this. Let me give you a quiz. Let's think about it as a quiz. Give me the thrust calculations for this type of engine. We have an inlet. You don't need to submit the results to me. Just do the calculations. Whoever gets the correct equation will get a bonus point, right? And you need 4 bonus points to not to submit one homework. 4, not 1. Okay? And I guess to make it harder for some people in the class, you cannot apply this to your previous homeworks. How do you think? What do you think about it? Should we apply it to?
I think we're getting late this
What do you do that way they want to get?
I mean, the way I look at it is we can either exempt from doing a future one, or we could replace our lowest grade.
That's a good point. That's a good point. Yeah, yeah, sure.
I like that, Drew.
Let's do that. Let's do that.
That's proactive.
Let's do that.
I like that a lot.
Let's do that.
Retroactive.
So this has a bypass, right? This is your fan. This is a very huge fan, right? Some of it is going through this exhaust. Some of the air is going through this exhaust and around the rocket, around the jet engine. And some of it is going through the station 9, which is the engine exhaust. So we have a bypass, right? I guess this is going to give you a good idea of how to apply the momentum equation. Yes?
Does it say 19 or 1A?
19. So this is a different system then, right? We have the jet engine here, 0, 1 through 9, and this one is just a bypass of the jet engine. It doesn't go into the jet, right? It goes just around the jet. But it also has some contribution to the thrust, right? Because of it has its own exhaust velocity, all of these things, right? This configuration is called the fan, front fan configuration.
This is pretty common, right?
Yes. What do you mean by pretty common? It is used a lot in a lot of aircraft, especially the commercial airline. Pardon me? What's that?
That bypass is enclosed, like, so there is a controlled volume, basically. Like, there's no MS.
Bypass is part of the engine.
Okay,
Right.
okay.
It's part of the engine.
So, I guess not my part of the quiz, but our control volume is just going to be around the fan and not extended beyond the fan.
That's what I was.
You can extend it beyond the fan. Your control volume is an arbitrary volume in space. You just have to make sure you are including whatever that is necessary in your analysis, right? You just have to have the correct inlet and outlet. Yes?
I think they're talking about open rotor concepts versus like turbofans. This is a turbofan.
No, it's just-
the last one, we had that extended around the engine to have
Yeah,
that
MS.
MS part, so.
That's what I was.
So you can actually, I don't want to get into a discussion about control volumes. You can do whatever you want to do as long as you understand the correct inlets and outlets, right? And I mean, you don't really need to, for this specific problem, you don't really need to start from the momentum equation. Just look at the thrust equation. One part of it talks about the exhaust part of your engine, one part of it talks about the inlet part of the jet engine, and then one part is the pressure area, and see how you can change that to fit this specific problem.
You want us to call the bypass air M.S?
No. But M.S is M dot of surrounding, something that is not included in the jet engine.
So B. Like M.B.
Yeah, M.B should be fine. Wait, what? Okay. Wait, it has a station number though. Why would you want to use M.B?
That's a good point.
You just M.19, right?
I'm too deep in now. I've written it once.
That's all right. That's all right. Okay. Since we don't have any, I wanted you guys to be very quick, as we don't have enough time, but I'm going to give you the equation. So the thrust, the uninstalled thrust here is going to be, do you have the answer?
Oh, I thought we were doing the whole
No. I
That's
told you just to change the thrust equation at this point. That's. Didn't I say that?
Do we have exhaust plus fan minus power fan?
What are you doing?
Bottom part.
What is VG? That's V9, right? Oh, that's 9?
That's 9.
M dot O plus M dot V9. You are close, but there are some problems though. Sorry.
Probably the pressure.
We'll get there. Okay, so the uninstalled thrust. The first part, let's do the inlet momentums. Or let's do the outlet momentums, I'm sorry. The outlet momentum. At the station 9, we are going to have M dot naught and M dot F, right? What about the station 19? Just M dot naught. There is no M dot F there, right? Because that's the idea. There is no combustion in the bypass. It just air bypasses the engine. That's it. So we are going to have M dot naught V19, or let's call it M dot naught, right? M dot 19, because that's just one section of V19 plus M dot 9 V9, right? And then you have to find the bypass ratio to calculate the correct ratios of them. But that's a simple. We're gonna do that later. Anyways, that's it. Let's do the outlet. Let's do the inlet momentum, the ram drag. The ram drag is just going to be M dot naught V naught, right? Nothing has changed about the inlet. What about the pressure areas? Pressure area is going to be P9 minus P naught A9 plus the pressure area of the bypass. P19 minus P naught A19.
I got the last pressure drag. The convention wrong.
The only thing I got wrong was that I didn't label the bypass as M naught. I just had it as something else.
That's
So on the first version of this equation, we had M dot naught plus M dot F in parentheses times V9. So why don't we also have that here?
I'm sorry, can you?
Well, we have like a.
You just made it M dot 9.
So over there, it's just M dot 9, right? But you have to keep in mind, this is actually, it should be M dot 1, not M dot 9. This is going to be the M dot of this inlet. It is not M dot naught anymore, right? Because some of the M dot naught is going through the bypass. Not all of it is going, not all of the incoming stream tube is going into the jet, right? Some of it is going to the bypass. Does it make sense? So you have to have the bypass ratio to find the ratio of these M dots and find the correct M dot that is going inside the jet.
Oh, okay. I see. Did you combine M dot 1 and M dot F into M dot 9?
Yes.
Okay, that's where that makes sense. Okay.
So
Yes.
in the exam, we're gonna get numbers instead of building it on a variable? Or?
Yeah. I mean, the questions for these chapters are so lengthy that there is no way for me to give you a parametric study, except for the momentum equation one, which is going to be a very simple one. Just have to start with the momentum equation, right? So yeah, make sure you have enough practice for the exam because it's going to take time. I don't want it to be like the flight mechanics exam you had. Okay. So if there is no question, let's move on. Let's actually talk about this. Just one thing. What would be the thrust formula during takeoff? Just a regular thrust, not the turbo fan. Just this thrust formula. What would it be during takeoff?
M dot 0 is 0.
M dot 0 is not 0. It can't be, right?
The entrance velocity is 0, so.
Yes, it is 0. Do you want to add anything to it?
Is there no pressure area?
You have no input.
There may be no pressure area, but we don't know that. But there is no, yes.
No, I was going to say no inlet momentum, but I think somebody else.
No inlet momentum. As Drew and Karim and Zach said, There is no inlet momentum because there is no inlet velocity. It is not moving yet during takeoff. Or if it's moving at a very low velocity, right? So we can assume that V naught is 0. So your thrust is going to be m dot f, m dot naught plus m dot f, V naught, whatever. It essentially is going to be m dot 9, V9, because there is no m dot naught at that point, right? There is, I don't want to, m dot 9, right? Okay, so let's move on. We talked about the installed thrust. If you go through my notes, there are some discussion about how to do the drag calculations for the pylons and nacelles, but that's just the regular integration of pressure and also momentum, that is the momentum deficit that is caused by the nacelles and the pylons when you install them. But if you ever were to deal with those, you will have a number. You don't have to do the integrations, right?
Would the pressure on the weight, would that affect the pressure of the outlet of the engine? Is there pressure?
There is. Let me tell you this: understanding and analyzing the interactions of different parts of body with each other is a very complicated part of aircraft design. That is going to be if we ever had to teach a course, it definitely will be a graduate level course, right? So yes, definitely. And that interaction, understanding the interaction, is a very complex part. Okay, so let's move on to, I guess we couldn't finish this chapter. Do I go too slow? I have to pick up the speed some. But we can, the idea, I don't know, should we start this or should we do it next? I guess there is like 10-15 minutes of material left. And no, let's talk about it next on Wednesday. Hopefully we'll finish this on Wednesday very soon. And then we'll go to solving some example problem. Not on Monday, I'm sorry, there's no Wednesday. Monday. And we will do some example problems. Your homework is posted. You should be able to start the homework at this point. You should be able to calculate, do the thrust analysis, all of those things. But you won't be able to finish the homework. Of course, you can go read the book and finish it. Yes?
During takeoff conditions, is it always a perfectly expanded nozzle? Because P9 is 1 atmosphere, P0 is 1 atmosphere?
It usually, so let me ask you this. What type of flow regime do we have during takeoff conditions?
What flow regime?
Yeah, is it subsonic? What did we say about the subsonic flow?
Oh, it's usually expanded.
It is always perfectly expanded. Huh? In theory, no, but in reality, in practice, yes.
So what if you drop something, like say you launch a missile, like one of the hypersonic missiles that has an intake from a jet that is already supersonic?
I guess it's not really takeoff.
It's not takeoff anymore, is it?
For the missile, is that considered a takeoff?
Takeoff.
Actually, that's a good question.
It's like a hypersonic missile. The technical part.
Yeah.